So we will start with some selected questions from HCV. We'll start with question number 10. So it says that the angle between the resultant contact force and the normal reaction exerted by a body on the other is called angle of friction. It says the angle between the resultant contact force and normal reaction is called angle of friction. So we have to show that if lambda is the angle of friction and mu is the coefficient of friction, in fact static friction, then lambda is less than equal to tan inverse mu. Okay. So let me explain the question to you, then you can try working this out yourself if you haven't done this before. It says that if you have a body, let's say, lying on a rough surface, so it has coefficient of friction mu, including static friction. Now, let's say some kind of external force is acting on it. So as a result of that, the other forces acting on the body are weight, normal reaction, and friction. So it's a general case, so we can take friction can be both things. It may be that the body is at rest, so friction is static friction. It may be the body is in motion, so the friction is kinetic friction. Whatever be the case. Okay. Now, the resultant of F and N is called the resultant contact force. So this thing that they've explained here, this is the resultant sum of normal reaction contact force and friction, because both of these are contact forces. These are both different types of contact forces. So if you talk about resultant contact force, it is the net contact force, so it's the resultant sum. So on the body, you can see that the resultant contact force will be the vector sum of normal reaction and friction. So normal reaction and friction are the contact forces. Okay, so their vector sum They'll always be perpendicular to each other because one is tangential and one is normal. So their vector sum will be a force which is like this. Let's say we denote that with R. So their vector sum R is the resultant contact force. And this angle is the angle of friction. Okay. So what we have to show is that this thing, lambda should be less than equal to tan inverse mu. So try this out now. Very good. Okay. So you can see that because normal reaction is perpendicular to friction, so that means R being n plus F, R's magnitude will become square root of n square plus F square. So therefore, since F's maximum value is mu n, therefore R's maximum value is okay, and F's minimum value is 0. So R's minimum value is n. And also you can see from the triangle that tan lambda is equal to F by n. So lambda is equal to tan inverse F by n. So from this, you can also understand that lambda's minimum value is 0 when friction is 0, and lambda's maximum value is tan inverse mu when friction is mu n. So lambda is in between tan inverse mu and 0 in any given situation, whereas R ranges between this and n in any given situation. Okay, so this is a more complete inequality over here, but in the given question, you have to only prove that lambda's upper limit is tan inverse mu, which you have done. Okay, so make a note of this in case you haven't done this. Okay. Okay, next we'll move on to question number 15. So go through the question if you have the book in front of you. I'll explain to you. Yes, Prince, you have some doubt? Yeah, I'm doing some selected questions from H.C. Verma, but if you have some doubt in a question before 15, you can ask me. We will discuss that also. Okay, we'll discuss question 14 also then. Okay, so let's do that immediately after question 15. Okay, so come to question 15. So what it says is that the coefficient of friction between the shoes of an athlete and the ground is 0.9. So let me excuse the poor drawing, but the coefficient of friction is 0.9. Okay, so what happens is that when when you're running and you're pushing forward, okay, how you're pushing yourself forward is by you're using your muscular force to push your leg backwards. Okay, so the friction acting on your foot becomes in the forward direction. Okay, so typically when you're taking a step forward, your forward foot is not on the ground, it's lunging forward, so only your backward foot is on the ground. So the normal reaction acting on it is equal to your weight. Okay, and the friction is a static friction. So the acceleration your body has at that point of time is equal to static friction upon m. So the maximum acceleration you can generate is maximum static friction divided by your mass. So that is mu n divided by m. So that will become mu mg. I mean, okay, the maximum acceleration, because normal reaction is equal to mg. Okay. Now the thing is that the amount of static friction generated actually depends on the muscular force generated to push your leg backwards against the ground. Okay. That's why in general it will be less than equal to mu n. Okay. So that's one thing. Secondly, this acceleration will not be continuous because there is a time interval between one leg hitting the ground and another leg hitting the ground. Okay. There is a gap of delta t between alternate feet pushing the ground back. Okay. So during that gap delta t, there is no acceleration. Okay. So that is where the whole Superman thing comes in. So the lesser the stride gap time delta t and the larger the static friction generated, okay, the more will be the average acceleration. Okay. So for Superman, who's superhuman, we'll say delta t tends to 0 and maximum always. Okay. So your average acceleration will tend to become mu g. So that's why. Okay. So now S is equal to 50 meters, U is equal to 0. So this time will be the minimum time. Okay. So that is the A part of the question. You can solve it by this. Just substitute this value of S and this value of acceleration. And for the B part, what is happening is that his velocity will become square root of 2as or at. So now he has to decelerate to stop. Okay. So again, the maximum deceleration that will be equal to again mu g, because now it's like the reverse action. To decelerate, static friction is acting on your feet backwards. So therefore, time taken to stop that is the minimum time, will be again become this much. Okay, so this is how you will calculate the B part of the question. Just make a note of this and next move on to question number 14. We'll discuss that. And question 14, notice that the coefficient of friction is greater than 1, which becomes possible for rubber tires, okay, because they're designed that way against concrete, against rough concrete surface. But most ordinary materials will have a coefficient of friction less than 1. Yes, that's correct. You can check the answer in the given answer key also. Okay, so if you finish working out both the parts, the answer will come out. See, the thing is that the amount of acceleration is equal to the amount of deceleration. If you assume that he's continuously maintaining the uniform acceleration and then continuously maintaining uniform deceleration, you'll realize that his velocity time graph will be like this. So obviously it will be symmetrical. No? So it will take same amount of time to accelerate and reach his destination as the time taken to decelerate after that to stop. So his velocity time graph will look like this. So let's say this is time t1. So this t2 will just become 2t1 because here the acceleration is that a max mu g, and here it's a deceleration actually. Okay, but t1 is when he reaches the displacement of 50 meters. Yeah. So you'll also see the total distance you will cover in that case will become 100 meters. Okay, so hope this question is clear. Now let's move on to 14th question. So what's happening, Prince, in this question is that the friction coefficient between the road and the tire of a vehicle is 4/3. So we have to find the maximum incline the road may have, so that once hard brakes are applied and the wheel starts skidding, the vehicle going down at a speed of 36 kilometers per hour is stopped within 5 minutes. So if you visualize like the situation over here, so this vehicle is having a speed of 36 kilometers per hour. So in fact, we can call this the initial speed. The initial speed of the vehicle is 36 kilometers per hour, which is the same thing as 10 meters per second. Okay. When the hard brakes are applied, so it starts skidding. So when it starts skidding, this is kinetic friction that acts. So that is mu n. So as a result of that, it will start decelerating. So you'll see the deceleration will come out to be how much? It will come out to be mu g cos theta. Yeah, because normal reaction is mg cos theta. Kinetic friction is mu n. So it will be equal to mh. So that is what your free body diagram will show you. Right. So now under this deceleration, we want that it should stop at a distance of how much? A distance of 5 meters. Okay. So v square is equal to u square minus 2as. We want 0 should become 10 square minus 2a into 5 meters. So from this, we know that we want the acceleration to be 10 square divided by 10, or 10 meters per second square. So we want mu g cos theta to be equal to 10, where g is 10 and mu is, how much is it now? 4/3. Okay, the coefficient of friction given as 4/3. So we'll take it as the coefficient of kinetic friction only. So there we are. Understood now? So 4/3 into 10 cos theta should be equal to 10. So theta should become cos inverse of 3/4, or cos inverse 0.75. So you can leave the answer this way, or you can also look it up in a scientific calculator or a table. That is about 41.4 degrees. Okay, so Prince, hope the question is clear. In fact, question number 16 is also based on the similar kind of thing. You can try it out later if you haven't done. Oh, wait. I made a mistake here. Okay. Just a minute. I made a mistake here. This is not correct. What will happen here is that this is why we should always make the proper free body diagram. What will happen is on the body, there is this also, no? There is mg sin theta, mg cos theta, normal reaction, and for hard braking there is kinetic friction. Okay. So the deceleration that the body will have will be kinetic friction minus mg sin theta is equal to ma. Okay. So now you solve this. So you'll get the acceleration, the deceleration as g into mu cos theta minus sin theta, or that is 10 into 4 by 3 cos theta minus sin theta. This will be the deceleration. Okay. And now given the kinematics, we want that deceleration to be equal to 10 meters per second square. This should be the deceleration. So now you connect these two equations. So your 10 should be equal to 10 into 4 by 3 cos theta minus sin theta. Okay. So that means 4 by 3 cos theta minus sin theta should be 0. So it should be 1. Now you can use that trigonometry thing that we were doing yesterday. No? So this term now, this can be written as like, you know, a sin theta plus b cos theta can always be written as root of a square plus b square into sin theta plus alpha, where alpha is tan inverse b by a. Remember we were discussing about this yesterday. So this term can be written as, so here a is minus 1 and b is 4 by 3. So square root of a square plus b square is how much? 5 by 3. So this can be written as 5 by 3 into sine of theta plus something is 1. So sine theta plus alpha is 3 by 5, where alpha is basically how much? It is tan inverse of minus 4 by 3. Okay. So theta plus alpha is sine inverse 3 by 5, which is 37 degrees. Okay. And here you can see that we have done the substitution here such that your cos alpha is 4 by 5 and sine alpha is minus 3 by 5. Okay. So alpha is in the second quadrant. No? So alpha is going to be 180 minus right. Okay, so minus 3 by 4, my mistake. Okay. Actually, you can do something simpler here. I'll explain. You can take LCM 3 first. So this whole thing will be easier to solve. Just take LCM 3 on this side now. So make this equation 4 cos theta minus 3 sin theta is equal to 3. Take the 3 that side. Now multiply, divide by 5. So when you multiply, divide by 5, you'll get 5 into 4 by 5 cos theta minus 3 by 5 sin theta is equal to 3. So this, as you can see, will become, now use this formula. No? This is like, this is cos 37, this is sin 37. Okay. So 5 into, you can use the cos A cos B formula. The cos A plus B formula basically. Okay. Instead of that, now you can use that. So this is cos of 37 plus theta is equal to 3 by 5. Okay. So that means 37 plus theta is cos inverse 3 by 5. Then you don't have to worry about all this obtuse angle, second quadrant and all that now. It's a little bit easier. Okay. So basically to get from here to here now, what we are doing is we are multiplying, dividing by 5 by 5, the whole equation. On the left hand side, we're doing this. Understood? So that's a little trick we are using. Okay. So now you can see that 37 plus theta will become 53 degrees. So theta will become 16 degrees. Okay, so you can do it by using the standard formula also, but it will just become a little bit more cumbersome, the calculation and all that, because you'll be dealing with an obtuse angle in the inverse circular function. So sometimes you can just use a variation of the standard formula in developing the equation. Okay, so finish writing this down, and after this we'll be doing question number 19. So if you finish this, go through the question number 19 and start making the free body diagrams of the two objects in it. We will discuss that next. Okay, we will do that also, friends. Okay, so there's a bit of similarity between 18th and 19th question. Both can be understood by the same set of concepts, so I'll explain. So, the first thing we need to figure out here is that on an inclined plane of any arbitrary angle theta, if we get a combination of two blocks like this, which are connected by a light rod, so in what situation there will be tension in the rod and what will be the direction of the tension? We need to figure that out first. Okay. So let's start with the case which is given, that there's a common coefficient of friction for both of them. Okay, so we take that case where coefficient of friction for the first block is equal to coefficient of friction for the second block. Okay. So both blocks are made of same material. Then you will see that on their own what is happening. Suppose I had not connected them by a rod. Suppose I had just released them like this. Okay. Then independently, also A1 would be equal to A2, which will be equal to G into sine theta minus mu cos theta. Right, this point is clear to all of you, because the free body diagram would consist of forces mg sine theta, mu n, n and mg cos theta. No, it will not be, na? Because वही हो रहा है देखो ना, your acceleration is independent of mass. It depends only on coefficient of friction. Just write the equation here, you will understand. Mg sine theta minus kinetic friction is ma. So this gives you this, no? So it doesn't matter that one is heavier than the other. Okay. So independent of the masses, what will happen is that they have tendency to independently, they have same acceleration. Okay. So therefore, what we'll understand is when connected by a rod, neither pushing nor pulling happens. They have a tendency to have the same acceleration. No? So the tension in the rod will be zero. And they will have a common acceleration of g into sine theta minus mu cos theta. So this question is done by this much. Okay. But we will do a second part of this question also. Now suppose mu1 was greater than mu2. That is, this block had a larger amount of friction compared to the other block. So then what would happen is, independently, if you release them, then A1 would tend to be less than A2. A2 would tend to be greater than A1 independently. Okay, because mu1 is greater than mu2. So the one having more friction will tend to have less acceleration. Okay. So in this case, what would happen is, if you connect them by a rod, M2 has a tendency to accelerate more, no? Because coefficient of friction is less. So M2 pushes the rod. Okay. So the direction of tension will become like this, become outwards, which cannot happen if it's a thread, but because it's a rod, it can happen. Yeah. Now we can calculate what this acceleration is by making the individual FBDs. Okay. So if you make the, or you can make a combined FBD also. Okay. So you can make a combined FBD and understand that on the combined mass, you have a combined amount of friction F1 plus F2. And you have a combined component of weight giving it an acceleration a. Okay, so this a would come out to be like this. So you would have got this acceleration like this. Or you can take this also common outside. Like this, we could have expressed the acceleration. Okay. And then you make the FBD of one of the two blocks. Like for M1, you make the FBD. So you can calculate the tension. So you substitute this here, so you can find out how much the tension is. So this thing has not been asked in this question, but supposing it would happen, it would be like this. Supposing mu1 was greater than mu2, then this is what would have happened. Understood now? Now similarly, so you write this down, okay, and then you also figure out that supposing opposite of this happened, that mu2 was greater than mu1. Suppose mu2 was greater than mu1, then what kind of free body diagram we'd get, what kind of acceleration we get, and also what the tension would be like, how we'd figure that out. Okay, so understood now. So once you get this question, you'll also figure out how to do the previous question, the 18th one. It's very similar, but there are three cases actually, no, different values of mu1, mu2. So you'll realize here that if mu2 is greater than mu1, then independently m2 has a tendency to accelerate less than m1. Okay. So when they are together, m1 has a tendency to accelerate faster. So it will pull on the rod. So the rod will have a tension like this. That is the difference between this situation, because this implies that m1 tends to pull on the rod, because independently a1 would have been greater than a2. So the direction of the tension will be like this. Whereas the second case we had seen, when mu1 was greater than mu2, the tension was outwards. Why? Because m2 was pushing the rod. That is the difference. In this case, the tension is like this, because here m2 pushes on the rod, because independently a2 would have been greater than a1, but here both are having the common acceleration. Okay. So that common acceleration magnitude will come out to be the same. It will be g into sine theta minus mu1 m1 plus mu2 m2 divided by m1 plus m2, whole thing into cos theta. Be like this only. Okay. But here, for example, for m1's free body diagram, you can see m1g sine theta minus tension minus f1 is equal to m1a. So from this you will get the value of tension. Okay, so in this question, there was only the first part actually in H.C. Verma. So that is the answer, that tension will be 0 because mu1 is equal to mu2. But supposing we had these other cases, and this is what would have happened. So note this down and turn your attention now just to question number 18. So very similar concept we'll use in question 18. Okay. So just go through the question and the data of the question, and you will understand in which case the blocks will be in contact, in which case the block will lose contact. It's actually a little bit simpler than this question in that sense. Okay, so let's go through the 18th question now. So in the 18th question, this time what we have is that the blocks are in contact. Instead of being connected by a rod, they're just placed against each other in contact. Like this. Okay. And whatever M1 is given to us as 2 kilograms, M2 is 4 kilograms. Okay. Now in the first case, the coefficient of friction mu1 is 0.2 and mu2 is 0.3. Mu1 is 0.2, mu2 is 0.3. Okay. So you can see that mu2 is greater than mu1. So if you were looking independently, if you had kept the blocks like this, then they would have acceleration such that E2 would be less than A1. Okay. So that is why when you put them against each other, what will happen here is that M1 will tend to go faster, so it will push. So M1 will push this with some normal reaction, and this will push back, and they will have common acceleration. Okay. So here what will happen is that M1 pushes M2 with contact force N. Okay. And on both of them, there will be friction acting backwards. So they will have common acceleration. So that common acceleration will be this, where F1 will again be mu1 N1, F2 will again be mu2 N2. Okay. And then you can substitute that in the individual FBD to find N. So also write an equation for M2 or M1, whichever. So for M2, you'll have M2G sine theta plus N minus friction is equal to M2A. So substitute this value of A here. So you'll get the normal contact force. Which one? नहीं, normal reaction तो cos theta है ना बेटा. क्यों sin theta क्यों होगा बेटा? Cos theta होगा ना? Because normal reaction, this one, this is the weight's cos component ना? Right, so understood the first part ना? Now similarly in B part is the other way around ना? In B part, mu1 is 0.3, mu2 is 0.2. So here what happens is that A2 has a tendency of being greater than A1. So they will just lose contact na, here. So this will just set off with an A2 greater than A1. So there would be no contact force. They will now start going independently like this. So they lose contact. The blocks lose contact because A2 is greater than A1. A2 will be g into sine theta minus mu2 cos theta. Mu1 cos theta. Inclined plane, na beta. So normal reaction has to be like that. Okay, next we will discuss question number 21. So finish going through this quickly and come to question 21 next. Okay, so in question 21, what you do is you make the free body diagrams of the man on the plank separately and of the plank, and then apply the condition that maximum friction is acting on the plank, maximum static friction to prevent slipping. So you do that, you should be able to work out the situation. Okay, so the plank has a mass small m, the person has a mass capital M, okay, and he's pulling down on the string with some force. So if he applies a downward force on the rope or string or whatever, develops a tension equal to F. Okay, and that tension acts like this. So here you want static friction to keep the system at rest. Okay, so you make the person's free body diagram. Okay. So there is tension, is body weight, and some kind of normal reaction, let's say N1. Okay. And you make the Planck's free body diagram. Only this should be capital M. So his mass is denoted by capital Mg. Okay. So on the Planck there is N1 acting like this. There is its own weight, small mg acting like this. There's some normal reaction from the ground. There's tension from this side and static friction. So static friction should balance tension, but static friction is less than equal to mu n2. Okay. So from that you will get there. So just solve this and try to work out the answer yourself. Okay, so let's see the equations. So from the man's free body diagram, you can see you have T plus N1 is equal to capital Mg. So N1 is equal to mg minus T. From the Planck's free body diagram, you have N2 is equal to mg plus N1. So substitute this here. So N2 is equal to capital M plus small m into g minus T. Okay. And T is equal to static friction. Okay. That's your third equation. Now you put the limiting friction condition. Okay, that so T should be less than equal to this. Okay. So this T is the same thing as F. Capital F is equal to T. Okay, so finish this up and move on to the 3-block problem, question number 23. We will do the B part of that. Okay, so we will solve this question just like the method that we discussed yesterday for 3 block problems. Applying exactly the same method, just let's use the data of the question given. So the masses of the 3 blocks given are 7 kg, 3 kg and 2 kgs. Okay. The ground is frictionless. This is a smooth surface, but as usual, this has a coefficient of friction 0.3 and this has a coefficient of friction 0.2. Now in this part we are talking about you are applying a force of how much is it, 10 newtons on the 3 kg block. So we are applying a force like this of magnitude 10 newtons on the 3 kg block. So we have to find the accelerations of the individual blocks. So the method of solving is always the same, that you start with the assumption that there is common acceleration. But before that, you also find out the maximum frictions which are available. So on the block A, this normal reaction will be equal to its weight. Okay. On the block B, its own weight is 3g. So this normal reaction, okay, so N1 will become equal to this weight 2g. So N2 will become equal to 5g. Okay. And for the last block, now see what is happening. We are applying the external force on this one. So immediately there'll be friction like this here and friction like this here. Whereas on this there'll be friction like this. On this there will be friction like this. Okay. So if this block has some acceleration A1, this block has some acceleration A2, and this block has some acceleration A3. Now you can see that F1's maximum value is mu1 N1. So mu1 was 0.2. So zero point 0.2 into 2g. So that is 0.4g. So 4 newtons. Taking the value of g as 10. And F2's limiting value is mu2 N2. So F2 is less than equal to 0.3 into 5g. So that is 15 newtons. Okay, so this is important to understand that the limiting values of F1 and F2 are this. Okay, so this becomes the starting point for the question for us. Now next what we'll do is we'll start with the assumption that they have common acceleration. So assuming no slipping, that is A1 is equal to A2 is equal to A3 is equal to some common acceleration A, suppose, and F1 is static friction, F2 is static friction. Okay. So from the combined free body diagram, applying the force like this, you would get the common acceleration to be how much? F upon total mass. So that is 10 upon 12 or 5 by 6 meters per second square. So if they are having common acceleration, then this would be the value of the common acceleration. Yes. Okay. Now we need to check for friction. So to check on friction for this common acceleration, check F1 and F2 needed. So free body diagram of block A, you can see F1 is equal to mass of A into this common acceleration. So F1 will become 2 kg into 5 by 6. Okay, so that is 5 by 3 or 1.67 newtons. So this is fine because you can see that F1's limiting value was 4 newtons. So there's no problem there. Okay. But also look at C's free body diagram. So F2 is equal to mass of C into A. So the amount of friction required here is mass of C, which is 7 kg into 5 by 6. So 35 by 6. So that is nearly equal to close to 6, but something like this. Okay. So this is also available. Okay. Because you can see that maximum friction is equal to 15 newtons. Okay. So that means there will be no slipping. So therefore, the assumption is correct. So finally, this tells us that assumption of no slipping is true. Okay, so hope this is clear. Just make a note of this, people. Okay, we'll do a part also. So if what is happening is the accelerations are different, then you have to come to this free body diagram, and here the frictions will be kinetic friction. So in case of slipping, F1 will be equal to 4 newtons, which is kinetic friction. Okay, so A1 will become F1 upon mass of A. So 4 upon 2 meters per second square. Okay. F2, suppose there's slipping between A and B. Similarly, if there's slipping between B and C, then this will be kinetic friction. So it will be equal to 15 newtons. So acceleration of this block will become F minus F1 minus F2 divided by mass, and acceleration of this one will become F2 divided by mass of C. So it will all come from the free body diagram. Yeah, because that's a different situation. But वहाँ पे you are applying the force on E. See, part A of the question, it's different. You're not applying the force on B, you're applying the force on E. Understanding? I'm not giving the answer for part A. I'm telling you here, suppose there had been slipping occurring, then this is what would have happened. If you're applying the force on the block A, you have to make a different free body diagram for A. Okay, so for part A, you're applying the force on this one now. So there your individual FBDs will become different. इस पे force ऐसा लग रहा है. So this friction is like this. So F minus F1 will become mass of A into acceleration of A. And on B, this friction will act forward. This friction will act backwards. So F1 minus F2 will be this. Okay. So if acceleration of A is equal to acceleration of B, then F1 is static friction. So F1 should be less than equal to that value we had calculated above, 4 newtons. If acceleration of B is equal to acceleration of C, then F2 is also static friction. So F2 should be less than equal to 15 newtons. Okay. But on the other hand, if acceleration of A is not equal to acceleration of B, then F1 is kinetic. So F1 is equal to 4 newtons. If acceleration of B is not equal to acceleration of C, then F2 is kinetic. So F2 will be equal to 15 newtons. Okay. So this is the set of equations you can use for the part A. Just make a note of this also, people. Okay, so Prince, you understood how to work out this question. Very good. Okay. So we will practice these questions out before your test coming up on Sunday. The level of difficulty of questions will not be more than this. It's this much only. Okay, so just try it out, Prince. You will get the answer. Okay. B and C में slipping नहीं हो रहा है ना बेटा. So you make them a combined object. Take the friction F2 as the static friction and take acceleration of B is equal to acceleration of C. You'll get the answer. So in the second and third equation I've written on the right hand side, for acceleration of B and acceleration C, take the common acceleration, no? Because there's no slipping happening between them. So you'll get 4 minus F2 is mass of B into some common acceleration A, and then again F2 is mass of C in that into that common acceleration. Now solve that set of equations, you'll get the answer. Okay. Okay, people. So with that, we conclude today's session. So as I said, like just practice out the questions we have done in the last couple of days, yesterday and today, and you should be prepared for the test coming up on Sunday. Do a bit of revision of Newton's laws also because it's a common test. So constraint relations, system of pulleys, pseudo force concept, non-inertial frame. Do a bit of revision of all that, and you should be well prepared for the test. Okay, that's it for today. Thanks for attending, people. Wish you all the best.